So uh, what I'd like to present today is a tool that you can use in Excel, Microsoft Excel, which allows you to determine the components of a mixture when you're using absorbance spectroscopy or any other linear technique like Raman, for example, or FTIR, where the components come together in a spectrum, and the spectrum is all of these components overlaid. So the LinEst is the Excel tool, and LinEst does least squares modeling, right? And what least squares does is if you have data, XY data pairs or XXY data pairs or XXXY data pairs, etc. least squares will give you the coefficients B0, B1, and B2, where you can take B0 times X0 plus B1 times X1 plus B2 times X2, and that will nearly equal Y2, the Y value, right? So an example of that we're all familiar with is the slope and intercept of a best fit line. So you can take a scatter of data points, and you need a B0 value, which is multiplied by X0, and B1, which is multiplied by the constant 1, right? In this case, if you do the least squares analysis, B0 will come out, and B0 will be the slope, and B1 will be the intercept. You can also apply this to many other problems of a chemical nature, chemical physical nature, right? You can find the bond strength and bond length of a diatomic molecule from its rotational spectrum. You can find the rate constants and orders of chemical reactions and many others. And it's really boils down to finding a way to linearize the model, right? So here's
Mhm.
another example of linear model, right? And to review here, a linear model is one where the coefficients B0, B1, and 2 multiply various functions that are not embedded within them. So a linear function is y equals B0 times F0 of x plus B1 times F1 of x plus B2 times F2 of x, etc., right?
Mhm.
In the case of a line, you have y equals mx plus b. And this translates to y equals B0 F0 of x plus B1 F1 of x, where B0 is just the number, oops, sorry, B0 is going to be the intercept. I have to send you a new one. And F0 equals 1. And F1 equals the slope. Oops, sorry. F1 equals X. Sorry. Trying to edit here and talk at the same time. And B1 is M, and F1 of X is equal to X. So I'm going to nuke in this case. B0 is the intercept. Oops. F0 is 1. All right, I'm going to edit this guy.
And these are just functions, right?
Right, exactly. You know, one of the things about it is that all these f0 of x, right?
Mm-hmm.
It's just a constant. It's just the number one. You know, it doesn't actually there's no, it's like x raised to the power of 0. It doesn't matter what x is. It's always 1,
Yeah,
right?
yeah.
So uh so if your f0 function is 1, b0 will be the intercept, a constant, right?
Yeah.
And then if b1, if f1 of x is just x, right? Nothing modified, then b1 will be the slope,
Right.
you know? Good. So I'll send this also to you, right? But then you can also take other mashes of data, right? For example, if you want to look at the vapor pressure of a gas as a function of temperature, a good model for that is the Clausius-Clapeyron equation here. It says log p equals minus delta H over R times 1 over T, right? Plus a constant. However, if there's any enthalpy dependence in the delta H value, then you can also multiply it by A over R times the log of T, right? And so there are now 3 functions of x here. There's 1 over T, there's log of T, and there's the number 1, right? Which is just like T to the raised to the 0 power here, right? So
Yeah.
here we got y is the log of P, x is this set of variables here, right?
Yeah.
The set of variables is T to the minus 1, log of T, and the number 1. And the coefficients that come out here are going to be minus delta H over R, A over R, and some constant C,
Yeah.
right? And to distinguish it a little bit from the linear, from the equation where you have just a slope and intercept, when you have more than one function of x here, or more than 2 functions of x, they call it multivariate least squares, right? Just because there's more than one function of x in the data set for which you're deriving b values, b0, b1, and b2, right? And so one question you might have is, how does LinS find the b values, right? Because the y values are just a bunch of numbers, right? You calculate the pressures, take their log, and that's just a number. You calculate the temperature, take its inverse, that's a number. Temperature, take its log, that's a number. 1 is just a number, right? And what it's going to find are the b values that best fit this model here, right?
Yeah.
And this model is simply this model, right? There's no difference from the perspective of the least squares. If you have log p or just y, and delta H over R times 1 over T is just B0 times F0, right? And B0 will just come out, and whatever B0 will be a number, and you can calculate delta H by multiplying B0 by R, or by minus R, right? So that's how you'll find these numbers. But how does least squares find the numbers? Well, it's a little bit of a conversation, but in a general way, it's what LinS does is it finds the roots of a parabola that's formed by the guess values and the true values um, for example, the guess values might be B values, and then the true values are some unknown true value, right? And it simply assumes that these that this parameter here, x guess minus x true quantity squared, is an upward facing parabola. And that is actually true when you go into when you set up the least squares model. So then if you have multivariate models, what you do is you compute chi-squared here. And chi-squared is the sum of the
Honey,
differences.
hold on.
Yes.
The fridge is open, it's beeping. And I'm like, what is this beeping? And
Okay, go
about-
close the fridge, baby.
Here are some results.
I'm like, what is this sound?
It's going
I'm
ding,
like,
ding, ding, ding.
yeah. Okay, honey.
Yeah. So for finding two variables, m and b in the linear equation y equals mx plus b, you'll take your data set here, which is all these xy data pairs, and then you'll take a trial value for m and a trial value for b, and you'll compute this value called chi-squared, right? And chi-squared is the sum of this is the predicted y value, that's what the y value that would fall on the line, minus the actual y value, which is the actual y data point value, right? And it's the sum of the squares of those residuals. That vertical displacement between the model and the data point is called a residual. So chi-squared is the sum of the squared residuals. And so you can show that chi-squared, if you plot it as intercept and slope versus chi-squared, or I'm sorry, chi-squared versus intercept and slope, it gives you a parabola of revolution. And the minimum point on that parabola down here is the point where you have optimized the b values for the fit, right? You've optimized m and b, right? The slope and the intercept. And that gives you the minimum chi-squared, and that's what we're defining here to be the best fit line. And so you can see that here. Actually, we should go to, if you can do this, honey, you can go over here, and then you can show how changing the b value increases chi-squared until it hits an optimum, and then if it's too low, it increases chi-squared, right?
Yeah.
And then similarly with m values, right? That there's an optimum value of m for that fit. Okay. So this is how, this is basically how least squares finds the minima in these two parabolic functions simultaneously for this data set. So it's a little bit of matrix math. It's not too bad, but it's a subject for another day. So the way that you use the function here is that you'll have a little block of data called where you highlight these two cells. For example, we just want M and B. You'll highlight E29 and F29, right? Then you'll come up into the formula bar, you type equals linest, you give it the Y data, and then comma, the X data. If you want an intercept, you type true. And if you want statistics, you type true, or if you don't want statistics, you type false, and you close out by with Shift Control Enter. You have to be editing up here and type Shift Control Enter, and then it will fill these two fields with the results of linest calculation.
Yeah.
So now I want to show you the way that you can do this to fit an absorption spectra using linest. And here, for example, in this golden spectrum on the left-hand side, there's a lot of spectra, so just focus on this golden one on the left-hand side. This is the spectrum of a mixture of acetone, ethyl acetate, and toluene at unknown concentrations in acetonitrile. Acetonitrile doesn't present absorptions in this region, right? So now alongside this golden one, there's a blue spectrum here, which is kind of hidden under the gold one on the right here, which is the spectrum of 1% acetone. And there's a spectrum here in gray, which is a spectrum of 0.05% toluene. And then there's a spectrum here of 0.5% ethyl acetate. So there's a mixture and three standards, and we're going to presume that by adding up these three spectra using different coefficients, we can match this mixture spectrum, right? So we are in search of three values which make, by which we can multiply the acetone, the toluene, and the ethyl acetate, and arrive then at a spectrum that looks exactly like the spectrum of the mixture. Okay, so there's actually a little twist here, right? Because the formula, the linear formula that we're going to work with is the absorbance of the mixture as a function of lambda is epsilon as a function of lambda times C plus epsilon 2 times C2 plus epsilon 3 times C3, right? So what I'm going to do is I'm going to take each of these spectra and divide them by the concentration, and that will give us an epsilon value with units of percent per centimeter. And these epsilon spectra will then be multiplied by these values to produce a spectrum that looks almost exactly like this unknown mixture spectrum. So these, on this side here, what we have is the modified, now these are component spectra, right? So this is epsilon for acetone times the percentage of acetone that came out of Linest, epsilon of toluene times the percentage of toluene, and epsilon of ethyl acetate times the percentage of ethyl acetate, right? So when you add those up, you get what's called a component sum, right? The component sum is this dashed green line. And then the mixture is a golden line here. And you can see that they overlap almost exactly everywhere. So this is a greatly successful experiment. And we get 0.998% acetone, 0.3% ethyl acetate, 0.3% ethyl acetate, and 0.027% toluene, right? These are not the concentrations of the standards, but there are multiples of these values, right? And one thing that should be obvious to you by inspection is that the acetone standard and the sample have, out in this region of 280 nanometers to 320, have exactly the same form, right? That means that the sample and the acetone have the, that is the acetone standard, the acetone in the unknown mixture are the same concentrations. And this predicted 0.9987%, whereas this is exactly 1.00%. So this is effectively the same as this, right? The other values are significantly smaller in the B values that came out. So this is acetone, this is B0, B1, and B2, and they come out in this weird reverse order. So this is simply showing that you can decompose a mixture into its constituent parts using the standard spectra. And if you're curious as to whether is this actually a good fit, you can subtract the component spectrum from the model or from the unknown mixture here and come up with a residual. And this dashed black line is the residuals. So it's the tiny differences between the dashed line and the golden line here, the mixture and the component sum. If we subtract these values here, we come up with this dashed line here, which is plotted on the right y-axis here, because the numbers are very small. And you can see that it's slightly imperfect, but it's not bad at all in terms of determining wavelengths or in terms of determining these component quantities. So that is all we got for today. Any questions, you big dummies?
Roger.